let's use what we learned about mass. During the summers, I teach courses for high school teachers. They come from all over the country, and we've had people come in from other countries. And during those classes, we make them build the physics from the ground up in a very careful way. And we do some detailed experiments. One of the experiments we do, two of them actually, is about Newton's second law. What they do is they take a mass and they exert a force on it. Now, because teachers have very low budgets, they don't have much money to spend, we teach them how to make force probes that have, it's just a meter stick with a long rubber band on it. And the stretch of the rubber band is proportional to the force. We find that that object accelerates. Then they take that same object and they exert twice the force on it. They find that the object accelerates by a greater amount. When they do careful measurements, they find out that the acceleration is twice as greater, if that's grammatical. Okay? So what they find is that acceleration, fish, net force. It's proportional. If you double that, you double that. Okay? Now the next experiment they do, they start with the original, the mass being pulled by the force. They find the acceleration. And this time, instead of doubling the force, they double the mass, the amount of stuff. And what they find is that the acceleration gets smaller. Indeed, with careful measurements, they find that it gets half as big as it was before. So that tells us that the acceleration is inversely proportional to the mass. Now, if we take those two experiments that I wish we had time to do with you, but we do not, you'll just have to take my word for it. If we put those experiments together, we get this relationship. The acceleration is directly proportional to the net force and inversely proportional to the mass. Anytime I have a proportionality, I can replace that with an equal sign, provided that I include a constant. That proportionality symbol doesn't mean that the right is equal to the left. It just means that if I double the right, I double the left. So I have to put a constant of proportionality in there. Now, that constant, the size of that constant depends on which units I'm using. I've already defined my units for acceleration. That's meters per second for each second. It turns out that the units of mass are defined in terms of kilograms, where a gram is the mass of 1 centimeter cubed of water. We'll talk about that down the road a little bit. But that's been fixed. The thing that we can play with here are the units of force. Now in our country, in America, we use units of pounds. But we are the only nation on earth that does so. Everyone else has chosen to use newtons. And the newton is just the right size to make that constant equal to 1. And that makes the equation so much simpler. The equation then looks like that. And we call that Newton's second law. Now, the way you read that, the way I would like you to read that is a net force causes a mass to accelerate. But this also, the equal sign also means the value on the right has to equal the value on the left. And this gives us the answer to that question, how loud does my force diagram scream? How big is my net force? Well, it's mass times acceleration.